Did I pronounce your name correctly? Yeah. Okay, so we will start with Yuri Thamsten. I'm so very sorry about that. So we will speak about local null controllability of a class of non-Newtonian incompressible viscous fluids. And so for the public, please close your microphone and your camera for the connection to improve. And so Yuri, thank you.
So thank you for the invitation. Thank everyone who took the time to come and watch. I will talk about this joint work with Pitágoras de Carvalho, Juan Limaco, and Denilson Menezes about the local non-controllability of a class of non-Newtonian viscous fluids. So this is the outline of the talk. I will first introduce the model, then provide some motivations for why we consider this model and the aspect of controllability. And then I will state the main result and describe some consequences following from it. And then for the most part, we will focus on the proof of the main result, and we'll finish off with some perspectives, so extensions and some small improvements we can make. So the starting point is this: we have a fluid within a certain region, capital omega, the velocity field of the fluid is y, and the pressure p. With a standard physical derivation, if we act distributively with a control v in a small subregion omega of capital omega, we derive this model. So here, capital dy, capital dt is the material derivative, and script t is the stress tensor, so minus the pressure times the identity, plus the shear tensor. And the constitutive law we assume here, if we were to assume nu to be a constant, we would be considering Navier-Stokes equations. Here we actually assume that it is of this power law type. So, and for technical reasons, we assume the exponent is either 1, 2, or at least 3. I will touch a bit upon that later. An alternative derivation of this model is to assume that U is the velocity field of a certain turbulent flow, and we can consider a local average of U around each point t, and for each time around each point of the space x, and each time t, and we take the corresponding average on the Navier-Stokes equations. And then we make this assumption that the average of this advection term is the advection term of the average minus the divergence of this Reynolds tensor, which we assume here to be of this form. For r equals to 1, this is known as this Magarinsky turbulence model. We consider some more general values of r. I'm considering the gradient directly, but you can still, everything that I will talk about here still works if you consider the symmetrized version of the gradient, which is more realistic. So now, in the part of the motivations, I will state some properties of this class of models. So first, there are some opposeness results, which were established in the 60s by Lajenskaya and Jacques Lilion. For these values of R, these fluids are dilatant, and pretty much because of this Stiles fact, which is that they have this natural stabilizing effect. So if the gradient of the velocity field becomes too large, then the viscosity becomes correspondingly large in such a way that it dissipates rather quickly. It's also, you can see the references therein in this work I'm citing here, that there is a wide range of applicability in real world problems. So for instance, in problems in chemical engineering, glaciology, biomathematics, and geology. From a technical viewpoint, we have some motivations. The first would be if we are looking for a global controllability problem, it is common that a local controllability problem is a step towards it. Also, for the Navier-Stokes equations with the no-slip boundary condition, which we are assuming here, the global no controllability is an open problem as of today. So since we at least would in principle expect that we would be able to prove that these models are stabilizable for positive nu1 at least, if we can get some uniform stabilizability, this could shed some light on the open problem for the Navier-Stokes equations, for instance. And also more technically, in the literature for quasi-linear parabolic equations, the methods that are available do not seem to work if you assume that the quasi-linearity depends on the gradient of the state, and so we are able to circumvent this difficulty here. So this is our main theorem. Basically, given any terminal time capital T, we can identify a suitable topology, namely that of H5, such that if the initial data is sufficiently small in this topology, we can steer it by means of a distributed control to 0. Of course, we assume also that it is divergence free, the initial condition. So the outline of the proof that we will discuss a bit more further in a few slides is basically we consider the linearization around the origin, and for the linearization we obtain a control, and we can actually obtain a higher regularity for the control. And so using this high regularity, we get enough regularity to set up Banach spaces and phrase the problem as an inversion problem, so that we apply an inversion function theorem to conclude. And there is this third step, which is basically verifying the technical assumptions. So namely that the theorem is applicable indeed. So some consequences, first of all, I will mention, we consider distributed controllability. There is some standard geometrical arguments which can extend the result for local no controllability acting with boundary controls. You basically extend the domain such a way that the boundary minus the region in which you are on which you are controlling is contained in the boundary of the extended domain, and the distributed control you take is in the difference, so that the trace of the controlled state is a boundary control. We can also devise a numerical algorithm from our approach. It's basically a Newton-Raphson algorithm, but since the spaces we set up involve some weights and so on, it's a quasi-Newton algorithm actually. And we have a corresponding convergence result. So if the initial data is sufficiently small and our initial guess starts sufficiently close, so it can also be phrased as if the initial data is sufficiently small and our initial guess is sufficiently small also, then the iteration process is contractive. So in particular, it converges. I will not really delve into numerical considerations, but this is just a simple implementation of the algorithm. So it works here in the bottom left. I've put the two components of the control, the cuts x1 equals to 1/2, and here you can see the time evolution, and here is the state. So now entering a bit on the aspects of the proof, first considering the linearization. So L here is this operator dt minus nu zero Laplacian, and there's the adjoint system of this. This is a forced Stokes problem with a forcing F, and we are acting with this control V. We have this global Karlman inequality for the adjoint system, where these weights rho 0 up to rho 4 blow up as the time approaches the terminal time. And I'm also embedding here the observability inequality together. And so in order to identify the control for the linearized problem, we introduce this space P0 and this bilinear form on this space, which turns out to be an inner product on this space because of the Karlman inequality. And then we complete P0 under using the norm induced by B, and introduce this linear form, which is continuous using the observability inequality, so that we can apply the Riesz representation theorem to represent it in terms of B. And we do this because if we introduce this Y like this and introduce V to be minus chi times Z, where Z is this, we can verify that Y is a solution by transposition of the forced Stokes problem, linearized, which is the linearized problem of our original model around the zero trajectory. And so in particular, since V is L2, this problem has a unique weak solution, for instance, and Y must of course be this weak solution. And from the Riesz representation theorem, we get also this estimate, and since this weight rho 3 blows up as time approaches the terminal time, we see that V steers the initial data to 0. So this is a control for the linearized problem. Then we obtain some, we do some energy estimates. Of course, the most intricate part is to identify properly the weights to obtain this weighted energy estimates. But then using these estimates, you can get some regularity and decay for the control. So this is the first result, and we can obtain actually higher order regularity and decay for the control. I'm not really going to talk about the technical aspects, but in order, this is the outline of the proof of this result. So remembering that V is minus chi times Z, we define U to be zeta times Z and pi tilde corresponding pressure multiplied by a suitable weight. And for this U and pi tilde together, they solve this adjoint Stokes system with this HP now 2. So we just use a standard regularity result for the Stokes system if we identify these weights here properly. And to obtain the higher regularity results, we do a similar argument for zeta hat times zt and zeta hat times the Laplacian of z. Then having this high regularity and decay for the control at hand, we can identify more weights so as to get proper estimates for higher order derivatives of the state. But of course, this is not for free. We must make more assumptions on the source terms. So by the end of the day, we have made a few assumptions on the source terms, and we seem to need this restriction of y0 belonging to h5 to obtain this last estimate. And so now we are willing to apply this theorem. Here I have stated in the more abstract form, but the idea is that you have a mapping, a continuous mapping between Banach spaces, which is strictly differentiable, say at 0, and the derivative at 0 is bijective and continuous. Then you can locally invert it from the right, which means for h sufficiently small k, you can find some point such that h of e is equal to k. And then you can have a control also on the norm of the solution. And so the way we set up the functional spaces here are the triplets y, p, v. This v, we ask the properties that we were able to derive in the preceding results. And we introduce an artificial source term, which is basically the source term which makes y the solution of a forced Stokes problem. And for this artificial source, we ask everything that we needed on the source terms to obtain the weighted energy estimates we derived before. And then we define the norm in y to be the natural norm for this space. Also in this space, we must require the no-slip boundary conditions and the zero divergence conditions and the regularity for the initial data. And then this space F here, we use it to define the codomain of the mapping capital H, which is basically the space of sources and the space of initial datum. The space of sources, we must put all the requirements which were hypotheses in the weighted energy estimates. And so the mapping we introduce is basically this. So of course, we want this first entry to be 0 and the second to be y sub 0, which is the initial data. But first of all, we must check that it is indeed well defined. So it must map y into z. So in this first entry, the second entry is not really a problem. The first entry we break in 3 parts. So this first part is immediately seen to be that artificial source term, basically what makes y the solution of a forced Stokes problem under the control V. And then there's this other 2 terms. H3 is easier to deal with than H2, so we focus on H2. But of course, I will not go into all the estimates, but I will just talk a bit about where the restriction on the exponents appear. So here, if you make a pointwise estimate, for instance, in the Laplacian of H2, you can get an estimate such as this. So if you formally replace R to be 1, this term is not even here, so it vanishes. You can estimate directly and say that it does work. But if R is greater than 1, then the Laplacian being small would be a technical problem. Fundamentally, we don't expect it to really be a problem, the gradient of y being small. But if we want to estimate it more directly, we must ask for R to be at least 2 here. And we use these emotions. So mainly that H2 is continuously embedded in L infinity, and that H1 is continuously embedded in L6. And so we take the supremum in space of the gradient, and this is bounded by the norm of the third derivatives in L2. and the norm L6 of the second derivative is bounded by the norm H1 of the second derivative, which is in turn bounded by the norm H3. So altogether, we are able to obtain this estimate. And within this norm L2, we multiply and divide by the weight. And fortunately, what is left is 1 over a power of the weight, and this is bounded. So we can get this estimate. And by the weighted energy inequalities, this term here is bounded by the norm of YPV in Y. So we can deal with the remaining terms and prove that H is well defined in this way. And now regarding the differentiability property, for the main theorem, we only need to prove that it is strictly differentiable at 0. And we will see that the properties for the derivative at 0 will follow from the results on the linearized forced Stokes problem. So here also, if we wanted to establish a local exact controllability to trajectories, then we would have to look at the adjoint system with this term included, right? So the linearization would include this term. So of course, if you ask the trajectory to be rather smooth, well, you probably will be able to prove a Kalman estimate for the adjoint system here. But for more realistic, say, the regularity we typically see in the literature with the no-slip boundary conditions, it is a more intricate problem. So here we focus on the case with a linearization around 0. And the way we prove it, basically, we consider 2 points and consider this difference. And basically, if the 2 points are sufficiently small, we're going to show that this difference loses to some epsilon times the norm of the difference of the points. Since this difference is equal to this, it is clear that it is enough for we to establish this estimate, because this bounds the left-hand side before. So again, now here I will just comment where the restriction on R being at least 3 or either equal to 2 or at least 3 appears. And namely, if you look at this first term, either you ask for R to be 1 or 2, so formally replacing, you can see that it vanishes, or we use a mean value theorem here, so it appears that an R minus 3 in the bound. So we need to ask for R to be at least 3, and then we can use the immersions just as before to estimate things. So if R is less than 3, everything goes okay, and we reach this final estimate. So clearly, asking delta to be sufficiently small, we can prove strict differentiability around 0. And then this is just the conclusion. So first of all, we have proven that the mapping is well defined and continuous, and in fact, strictly differentiable at 0. And the properties we need for the derivative, which are called lambda in the statement of the inverse function theorem, follow from our analysis of the linearization. And so we can apply the theorem and conclude that for every h, y0 sufficiently small in z, there is YPV solving this. In particular, if we take h to be 0, this is equivalent to asking that y0 be sufficiently small in h5. And then this equation clearly says that the PDE is satisfied, the initial condition is satisfied, and the no-slip boundary conditions and zero divergence are embedded in the space. And also, since y times a weight that blows up at terminal time is integrable, we can derive that it is steered to 0 by terminal time. So this was the proof of the main result. Now I will finish off just discussing some possible extensions. First of all, the first question that may arise is that if we are able to lower down this topology, so ask for less restrictive topology than H5, the way it is commonly done in the literature goes out more or less along the following lines. If we ask, say, the initial data to be sufficiently small in H, then we consider the uncontrolled state associated to this initial data, and if we can we can make estimates and conclude that there is a time where it belongs to H2 with a proper estimate. Then starting from H2, it will belong, say, to H3, and then you go on like this. The problem to apply this argument here is that it seems that getting estimates up to the boundary in this way for this class of models is not that straightforward. So it seems open. Some questions seem open as of today. But so another question is on the exponent that we ask to be either 1 2 or at least 3. And here, of course, if we consider functions nu a bit more general than what we considered, the method still works. So a possibility which seems to us to work is that you can regularize for the values of r between 0 and 1, or 1 and 2, or 2 and 3. You can regularize the function u so that it is differentiable around 0 with controlled derivatives. And in this case, you will be able to apply the theorem. And the point is just to argue how you can obtain the estimates on the control, which are uniform on this regularization parameter. And but it seems that the gradient being small is not a fundamental restriction. Now, regarding global no controllability results, if we are able to lower down the topology, what seems to be easier using local arguments is to lower down from H5, say, to H3. But to lower down from capital H is a bit more, it's a bit harder. But if we can prove the local no controllability result with the topology of the initial datum being capital H, then there are dissipation results available in the literature. And in this way, we would a large time global no controllability would follow. And now, about small time global no controllability, as I have mentioned at the beginning, it may be considering this system, we would expect that it is stabilizable. So it may shed some light on the corresponding problem for Navier-Stokes equations. But for the Navier-Stokes equations, and more recently for the Boussinesq equations, there is a method in the literature that people have used to establish the global no controllability in small time under Navier boundary conditions instead of no-slip boundary conditions. So it may be that the method used there, which is basically the smoothing, then stabilization, then local no controllability, or local exact controllability to trajectories. So it may be that for this broader class of models, this does work. But since this is already established for Navier-Stokes equations, it would be a more relevant result for considering this model per se. And that's the talk.
Well, thank you very much.
Thank you.
So sorry, it's difficult to get real applause these days. But thank you very much. So if there is any question, please feel free to open your microphone and speak. Or you can also use the chat, and I will tell the questions. So I think, Luz?
Yes, I think Enrique was speaking also. No? I don't know. I think that you are controlling all the components of the system.
Yeah.
Yes. So do you think it's possible to do as Corona and Guerrero in order to eliminate one of the components?
Yeah, I do think it's possible, yeah. Because we have used this Karlman inequality, and possibly as long as it follows more or less this approach, starting off from the Karlman inequality, I think it's likely that it still works. Yeah, but it would be harder if you were willing to prove the exact controllability to trajectories.
Of course. Okay, thank you.
Thank you.
Enrique, you had a question?
Yes, I was going to ask you about the exact control, local exact control. Before, thank you very much, because it was very clear and very good presentation. And I wanted to ask you about the local exact controllability to the trajectory. What are the main difficulties for extending the result to that frame?
So as I said here, when you linearize, of course, here we are linearized around the zero trajectory. So this term here, people have dealt with it in Navier-Stokes equations and so on, right? But then there's this term here, which is a bit more intricate. But I think that if you assume like the trajectory to be as regular as you want, probably you will be able to still establish the global Kalman inequality that we would need to prove the result under using the same method here for for controlling to a trajectory, to a given trajectory. But as I have said, it seems that in the obtaining estimates up to the boundary, it's not an easy problem for this class of models. So if you ask the more realistic regularity for the trajectory, then it might be a bit harder to prove the Kalman inequality.
Okay, and another question is when you spoke about the Boussinesque system, which kind of Boussinesque system are you thinking of? I mean, which is the structure of the diffusion term that you have for the temperature that you have in mind?
When I talked about the Boussinesque system, I think it's a preprint from you and some collaborators that you prove the small time global controllability using, it's an asymptotic expansion with respect to the viscosity. You make a rescaling in time and expand with the Navier boundary conditions. I was more like thinking of applying this method. Yes.
Yes, but in that system, the diffusion coefficient was constant.
Yes,
I mean,
sure.
here in the model that you are considering, if it comes from turbulence, in fact, you don't have a constant coefficient for the temperature. I mean,
yes.
I think there is an additional difficulty here.
No, yeah, surely there would some terms would appear maybe would perturb a bit more the boundary layer that pops up, but yeah, the main viscosity, like what is called the kinematic viscosity, is like the new zero, which like the inverse Reynolds, right?
Yeah.
And then this new one is like just as you said, like just a kind of a perturbation on the viscosity. So yeah, there's certainly an additional difficulty. But it's a possibility, right? I mean, if you, instead of no-slip boundary conditions, consider Navier boundary conditions, it might be possible to prove the small time global controllability, but it's definitely not trivial, of course.
Okay, okay. Thank you very much.
Thank you.
Okay, so maybe in the same spirit, I have a question on boundary layers. So do we have an accurate description of the boundary layers for these models with a very nonlinear viscosity?
Yeah, it seems that in these other references, they can characterize the boundary layers, or at least obtain estimates which are good enough to prove stabilizability. This is, I think, Professor Henrique Cara can correct me, but I think it's when they prove stabilizability, so approximate controllability, they make rescaling in time, so it becomes a problem in a large interval with a small viscosity. And then for the envisaged problem, they manage to identify and make, and that's the problem with the no-slip boundary conditions, is that you lose the estimates that you need for the boundary layer.
Okay, but there is some kind of description of the boundary layers in those cases, right? For Navier-Stokes, well, for the usual Navier-Stokes model, and probably for Boussinesque as well, right?
Yeah, I think there is.
But in your case, with the viscosity you have, does it exist?
No, yeah. I confess that I didn't make the computations, but certainly there would appear some perturbation, like on the boundary layer. I'm not sure if the estimates would still work well.
Okay. I think I've heard someone. Is there any more question? Well, Okay, maybe not. So if not, thank you again.
Thank you.
I'm the only one to applause, but okay. So we will shift speaker.
Let me stop sharing.
Yes.
Yeah, thank you. And Jeffrey Park, can you open your microphone and
hello, testing.
Hello.
Hi, Jeffrey.
Hi.
Hi.
Okay, so can you share your screen? Great. Well, so it's good.
Okay.
Okay, so let's start. Okay, so the next speaker is Jeffrey Park from University of Alaska in Fairbanks. So we'll speak about the inverse problem for the Schrödinger equation with non-self-adjoint matrix potential.
Okay.
Thank you.
Thank you. First, let me just thank the organizers and for the invitation and the opportunity to speak here. So I'm going to be talking about the inverse problem for the Schrödinger equation. And in particular, we're dealing with a non-self-adjoint matrix potential. So the setup of the outline of the talk is I'm going to introduce the problem as well as go through some initial things we need to talk about and go over before we start really digging into the main ideas of the solution. And then after, which will include explaining the method we're using and the two parts that are required to solve the problem. And then we'll finish with some concluding remarks. Okay. So the problem we're working with is this dynamical system. It's going to be system 1. It is a vector problem, vector equation. It's a vector Schrödinger equation. And Q is a matrix potential. And in particular, it's non-self-adjoint. So we're going to be dealing with a lot of difficulties that come up just because it's both a matrix and non-self-adjoint. And then we have a Neumann boundary condition, this ux 0t equal to f of t. And then we have a zero initial condition. So one other piece of information we have about this system is we have a response operator, which is going to be the source of our dynamical data. And what it does is we apply a control function to it, or we apply it to a control function, and then we can measure some information about the system on the boundary. And so the inverse problem is we want to recover Q using this response operator. And so so we're going to be dealing with the case where we don't know Q and we want to try and figure out what it is. And so some information about this problem. In the case of the scalar Schrödinger equation, this problem was already solved by Avdonen and others in 2002 and 2005. First solving it with a Neumann boundary control, and then later with a Dirichlet boundary control. However, the problem that we're looking at today is different and is much more difficult because Q is a matrix, and on top of that, it's also non-self-adjoint. So a lot of different issues come up because of these two problems. So this is a new problem. And then it's also a very good example to show off and kind of showcase the boundary control method, or BC method. And also, it's a good way to show how we can use both dynamical and spectral approaches to solve inverse problems. And then, so the first problem is Q is non-self-adjoint. So we have two differential operators we need to deal with. The first is just A, which is the negative Laplacian plus Q. And then we also have A star, which is the adjoint operator with negative Laplacian plus Q star. the matrix adjoint to Q. And so this is an issue that comes up because Q is non-self-adjoint, but there's also a problem that comes up because Q is a matrix. And the big issue here is we are not assuming anything about the eigenvalues of A and A star. And in particular, the focus would be the multiplicity of each eigenvalue and then the dimension of the eigenspaces associated to each eigenvalue. In particular, do you have enough eigenfunctions or whatnot? But for this talk, we're just going to assume that each eigenvalue has algebraic multiplicity mk, and then we have exactly mk corresponding eigenfunctions. In other words, the algebraic and geometric multiplicities of each eigenvalue are the same. And so we're not going to have to deal with root vectors or generalized eigenfunctions. However, in the paper that I'm so sorry, I forgot to mention that this is based on a paper with Sergei Avdonin, Alexander Mikhailov, and Viktor Mikhailov. But the paper, we have proved the case, or we have solved it for the general case if there are root vectors present. And then, so since we have this adjoint operator, we also need another system that involves it. So we have this associated dynamical system. The only difference is that instead of Q, we use Q star. And then just labeling differences such as using V instead of U, using G instead of F. And then we're going to equip this system with its own response operator, RT sharp. And it's defined exactly the same as it was for system one. So now we have these two systems that we're dealing with simultaneously. And so now we're just going to define, what space the operators work in. So we have this cal H or calligraphy H, which is just the standard L2 space. And then we have cal H1 and cal H2, which are based off of the Sobolev spaces H1 and H2. The only difference is here for cal H1, we have the right boundary condition being 0, so f of L is 0. And then for cal H2, we have that f prime of 0 is 0, and f of L is 0. And then so the domain of A and A star is this cal H2. And then another thing so this is kind of our initial setup into the. Do you have a question? What did I hear? So, so for the initial system, for these two systems, we have the control operators, which basically map our control functions to the target states, or the state, meaning it's the solution at time capital T. And so these are just standard operators that we have inside of the boundary control method. And then what they're used for will be shown a little later. So what is the boundary control method? Originally, or at first, it was used to solve similar inverse problems for wave equations, recovering the potential. And so it's been known for a long time that controllability is equivalent to observability. And then we use observability to get like identifiability, which then goes to inverse problems. And so there's this roundabout way to get from controllability to inverse problems. However, the BC method gives us this direct connection between controllability and inverse problems. And the reason why it was first used for the wave equation is because of these two key properties. The first is the finite speed of propagation. So we can, see how we can see the wave move throughout through the interval. And then the second is this causality property. And so because of these two properties, the BC method gave us a way to solve the inverse problem using a purely dynamical approach. So not even having to use, a spectral approach of any way, we could use purely dynamical information to solve the inverse problem. But that's for the wave equation. For the Schrödinger equation, we have infinite speed of propagation, and so a purely dynamical approach is not possible. So instead, we need to use we need to use kind of a spectral approach to get some information to mix with our dynamical approach, and then we kind of mix these two to solve the problem. However, using the spectral approach involves using the Fourier method, which then requires having a Riesz basis of Eigen Functions for the operators A and A star. Then we can have the Fourier representation and all of that. So the first thing we need to do is verify that the eigenfunctions of A and A star have the Riesz basis property. And so normally, or in the best case, if you have a self-adjoint operator, we have plenty of results in classical spectral theory for differential operators. In the case of non-self-adjoint operators, usually this typically involves investigating the associated Sturm-Liouville problem, which is also very difficult for in most cases. However, in 2015, Lunyov and Malamud came up with this new approach that uses a first-order representation of the Sturm-Liouville problem to provide information on whether or not a system has the Riesz basis property. And in particular, we use this result to prove that A and A star both possess Riesz bases of eigenfunctions. We're going to denote them by phi and psi. And just so that we're clear, in this talk, we're assuming that we only have eigenfunctions, but even in the case of root vectors, this result still holds that we get a Riesz basis of root vectors. So this is a very, very nice result that we have. But just having the Riesz basis property is not enough. We also need to be able to drive the system to each eigenfunction. And so this is called spectral controllability. So just a quick definition. For each eigenfunction, we can find a control that will drive the system to that state at time big T or capital T. And so we need to do so for both systems 1 and 3. And so that's what this WT sharp is, just the control operator for systems 1 and 3, which is just, you plug in your control function, you solve the problem, and then you set the T equal to big T for your solution. And then it should be equal to an eigenfunction. And so how do we prove that we have spectral controllability? Usually we use the method of moments, which involves using the Fourier representation and then deriving an integral identity and then obtaining a sequence of moment problems, and then we get a resulting exponential family, and then we need to analyze what properties this family has, such as minimality. However, the study of vector exponentials is a big issue. It's still underdeveloped, and we don't have enough information available to be able to use this method to prove spectral controllability. So instead, we use a technique that's called the control transmutation method. It's used by Miller in 2005. And the whole concept behind this technique is we use the controllability of the associated wave system, which is a very well-known result. And by doing so, we can construct the controls for the wave system with specific targets with a specific target state. And then using that control, we can do a transformation on it, which then gives us a control for our system with the Schrödinger equation. And so this method gives us the existence of controls, and then we can combine this work with we combine this result with the work of Ervedoza and Soaswa in 2010, which allows us to use controls from a smoother space. In particular, we have H1 0 0TCN. So the controlled transmutation method gave us L2 controls, but we can actually improve it to have H1 0 controls. So now we have, we've finally established that we have a chance to use the boundary control method, right? We've established that we have the Rees basis property. We've established we have spectral controllability. So let's begin. So we want to be able to recover spectral data using the response operators RT and RT sharp. But remember that RT sharp comes from a system that we've constructed ourselves. So we don't actually have it, but it turns out that we have access to it through an identity that expresses it through our original response operator RT. So that's what this identity, the importance of this identity is that we have a way to obtain RT sharp even though we don't know it originally. And then the next operator that we need is called the connecting operator. And the connecting operator is defined as this inner product here. So this is CTFG in FT. This is the space of our control functions. And it's defined through the inner product of their target of their states. So WT of F and WT sharp of G. And this is in the space H. And so, once again, we don't know Q, so we don't actually have WT or WT sharp. But it's an important fact in the boundary control method that this connecting operator can also be expressed in terms of our dynamical data, the response operator. And so we have this lemma that gives us this alternative representation using RT and RT sharp. And so we also have one that uses purely RT itself using the identity from the previous slide. So now we have this. Connecting operator. It's called the connecting operator because it does exactly what it says. It connects the space of controls FT with the space of states H. And so what is the importance of this control operator? And the answer is in our main result regarding recovering spectral data. And it is exactly that we have this generalized spectral problem and the solutions. So we have, this FKL dot is the time derivative and lambda K here and then FKL again. The solutions to this equation give us the spectrum and controls that correspond to eigenfunctions of A. So this equation itself will give us information about the spectrum of A as well as controls that will map to eigenfunctions of A. And so we can find find the eigenfunction, the eigenvalue, and all the eigenfunctions associated to that eigenvalue. And then similarly, we do have a result for A star. It looks pretty much the same, except we have adjoint CT star and then lambda K with a complex conjugate. This is another equation that we solve to find the spectrum and controls for A star. And so the whole point here is that we can use these two equations to obtain the spectrum. The problem, though, is that these controls that we get may not, in fact, correspond to a biorthogonal family of eigenfunctions, or we may not even have a linearly independent collection of eigenfunctions. And so this is the big issue that comes from our problem being a vector equation and Q being a matrix. This is the main problem that we have because of this property. And so now it's just a linear algebra exercise to be able to come up with an algorithm to construct families of controls that do in fact correspond to biorthogonal families of eigenfunctions. It's not really a big deal. It's just very technical, very similar to, say, a Gram-Schmidt process. And then you have to be very careful with how you choose things. Even in the case of root vectors, we do have an algorithm for that as well. So even in the more general case, we have an algorithm that works. So, we're just going to say I'm not going to state it. It's very long and very technical, but we do have it. And then we can obtain this new family of controls, F and G. And the eigenfunctions that they correspond to might be different than what we originally had with the phi and the psi. So we'll just label these new ones by phi hat and psi hat. And in particular, so once again, we don't actually have WT and WT sharp, but what we do have is RT and RT sharp. So we can apply RT and RT sharp to these controls, and we end up getting the traces of these eigenfunctions. So phi hat at 0 and psi hat at 0. And then we'll denote each of these by this capital phi KL and this capital psi KL. And so these two sets plus our eigenvalues will constitute our spectral data that we recovered. So, this is just the definition saying that, this is the spectral data we're using. And this is what we need in order to solve the inverse problem. So we got the spectral data. Next step is to use that data to recover the potential. And so, like I said before, the BC method uses the wave equation. So we have to construct this auxiliary wave system. And so it's going to look, almost identical to system 1. The main difference is that we're using W instead of U. And the second one is that we have this WTT instead of IUT. But it's, we have 0 initial condition. We have this Neumann boundary condition, and then a 0 Dirichlet on the other side. And we have, we give this system its own response operator. And then since we had a system for, we have an auxiliary system for system 1, we also need to construct a wave system for system 3 with with Q star. And then the solution will be called WG sharp. And then just like we did before, we can construct this connecting operator through the inner product of these solutions at t equal to big T. But before we do that, we want to use the fact that we have some spectral data. So, we're going to use the Fourier method, and we can represent our solution WF in terms of this series using the phi hats and these Fourier coefficients BKLT. And so each of these coefficients has the form of this integral. And so what is in this integral? It's this psi KL that we've gathered, and then the lambda K that we've gathered as well. And then similarly, we do the Fourier method, or we have a representation for WG sharp. And WG sharp also has this Fourier coefficient, and then this psi hat. But the focus is that this Fourier coefficient has this capital phi, which we have, and then the complex conjugate of lambda K, which we also have. And so, we have the connecting operator defined as normal, this, CTWFG, and then here it's the meaning in terms of H is WFXT, inner product with WG sharp xt. And then because we had this Reese basis property and a biorthogonal family, what we're left with in the end is just a series of the product of these two integrals. And so the first one uses capital psi and lambda k, and the second one uses capital phi and lambda k, which we've already gathered all of that information. So this connecting operator is completely determined by the spectral data that we've collected. And so what is the next step, and why did we figure this connecting operator out? First, we need to use controllability of the wave equation. And so we pick a very specific yjx. So ej is the jth standard vector in Cn, and then yj is the solution to this very specific equation. And then pjt is the control function that's associated, whose associated solution is going to match y up to t and then be 0 afterwards. So up until t, it's exactly y, and then after t, it's just 0. And the fact of the matter is that this control function, together with the connecting operator, satisfies a very specific equation. So it's this CTW PJT equals big T minus little t EJ. And then by the BC method, the connecting operator is boundedly invertible. So this equation has a unique solution for all t less than or equal to L. And then we can always find this PJT, and then we define mu j capital T by PJT at plus 0, meaning that we are collecting the initial jump in the control function. And it's an important fact that negative PJT at 0 is equal to, so the initial jump of our control function is equal to a yj at capital T. And so this function mu jt is twice differentiable with respect to t. And then we want to construct this matrix MT, whose columns are just the mu j's. And since each mu j is twice differentiable, M is twice differentiable. And then we have this equation that our matrix potential is equal to M double prime T multiplied by the inverse of MT. And the fact is that M is invertible except for finitely many points. So now we can just vary T within the interval 0L, and then we can obtain and recover Q in that interval. And when M is singular, we can just use the fact that Q is continuous to recover Q for those points. And then this will this will complete the process of recovering the potential. And so just some concluding remarks. So the original plan, or the original goal, was to develop a strategy to recover the non-self-adjoint matrix potential for the Schrödinger system, which we did. But in doing so, we both proved the Reese basis property of the operator A, as well as the spectral controllability of the system we were looking at. Also, we developed an algorithm that constructs control functions corresponding to Eigen Functions of A, and in particular, we wanted to construct the Reese basis that had a biorthogonal property. And so really, it's a very in-depth algorithm, and also takes into consideration the possibility of root vectors as well. One other note is the inverse data we used, RT, is a Neumann to Dirichlet mapping, meaning we apply our control function with a Neumann condition, and then our response operator itself is a Dirichlet condition, or Dirichlet boundary. However, by making some adjustments here and there, we can actually extend this result to include or not to include, but to apply to Dirichlet to Neumann mappings, which are also a very common result in or common problem in dynamical inverse problems. Okay, and that's it. Thank you very much.
Thank you. So yeah, again, I'm the only one to applaud. Okay. I'm sure that all the others are applauding as well. So there is one in the chat, for instance.
I appreciate it. Thank you very much.
Well, thank you for your very nice talk. So if there are questions, please feel free to open your microphone and ask.
Yes.
Oh, I think there are questions in the talk, in the chat, sorry.
Oui, Belassen.
And there's a question by Belassen as well. So, okay,
Yes.
Belassen, start, please.
I would like to know if there are at least a statement results in the dimensions.
I'm sorry, could you repeat that one more time?
Your result is in one dimension, space dimension.
Right.
Are there results in a dimension greater than one?
There are results for. Are there results? I am not actually sure. Not even in the case where it's just a scalar function in multiple dimensional space. That's already a very difficult problem, and so going into a vector equation with multi-dimensional space is going to be incredibly difficult to think about. I know Sergey is here. Perhaps he knows something about it.
Okay,
your Laplacian is of constant coefficient.
Right.
Okay.
Yes, I can know that there is a result in about inverse problem for the Schrödinger equation in multi-equation, but not for the matrix problem for classical dynamical scalar product for Schrödinger equation, not for the matrix equation. It is a result. My result is Belish of 2005.
Thank you.
Okay. So there are also questions in the chat by Christian Montoya. So Jeff, I let you read it.
Yeah, sure. 1 second. Can you apply this approach? So for the second question, there are indeed numerical methods to use the BC method to solve these potential recovery problems in general. We haven't implemented anything for our problem specifically, but for other problems that use the BC method, it's very common that we end up using numerical methods because we end up with a triangular system. And so it's very natural to use numerical methods to solve it, to recover the potential. As far as recovering an external source located in the right-hand side, I am not sure myself. It's just my focus has always been on inverse problems that have this form, so I don't really know much about other types. I believe so, just purely off of the assumption that it's already very similar to these kinds.
I can note that source problems can also be included into the scheme of the boundary control method, and it was done for several kind of inverse problems, not specifically for this equation, but for other equation with source problems. So it can be included to the same scheme. And source source may be recovered together with the unknown potential using the same inverse data. Using response operator, it is possible to simultaneously recover unknown coefficients and source function. If source function depends on x, or certainly only on x, not on t, certainly. Boundary control methods typically works for an unknown function depending on c, for autonomous system with coefficient independent of time.
Okay, thank you. So there's another question by Lassen Mania on the chat, who is asking about internal observations. And can you get some Kalman estimates to get the same results or similar results?
I'm not too well studied in Kalman estimates, but from what I understood is that you use these estimates to obtain controllability results or observability results. But what we're trying to do is we're using controllability to solve the inverse problem instead. And so perhaps you could use estimates to prove that you have the controllability requirements to use the BC method to solve the inverse problem. However, it's not something that we needed to use in order to solve the problem ourselves. Internal controls is also a similar problem. I believe, let me think. So using like an internal control for inverse problems is very similar in the case of boundary control. It's just typically boundary control is a more common type of problem that is dealt with, and so we kind of focus more on that. But having internal controls is not really such a big deal as long as the necessary requirements are fulfilled, such as the control being able to reach the entire space.
Okay, thank you. So are there any other questions? So it seems to be okay. So thank you again for this very nice talk. Also to Jeff and Yuri. So next week we'll have a talk by Belassen Deman, who is here. And are you going to speak, Belassen? Right now?
Yes.
Start next week, right? Okay. So again, thank you all. Take care and see you next week. Bye-bye.
Thank you. Bye.